In the name of Almighty God, I'm Mahsa Sankasha, and today I want to talk about larger scale structure formation. Today, the universe is very inhomogeneous on scales smaller than its present horizon. Take, for instance, the results of galaxy surveys, such as the one shown in Figure 1.5 top right, which corresponds to a three-dimensional map of a good fraction of all galaxies in the observable universe. Already by eye, one can resolve a variety of structures, lump filaments, walls, voids, which appear at different scales. Other astronomical observations, such as the Lyman alpha forest, weak lensing measurements, cluster counts, and etc., concur in establishing the picture of a clumpy universe. Simulations and observations suggest that worlds are a region which density is equal to 10 times smaller than the average. They fill 77% of the volume while containing only 15% of the total mass. Worlds occupy about 18% of the volume while containing about a quarter of a mass. Filaments provides the dominant contribution to gravitational forces. They occupy about 6% of the volume and contain about half of the mass. Lumps occupy a small sub-percent fraction of the volume and contain 11% of the mass. Quantitatively, from all these measurements, one can extract the matter power spectrum pK plotted in figure 1.5. Middle round right, it is defined via a delta K, and delta Capri is equal to 2p to the power of 3 pk delta to the power of 3 multiplied by K minus Capri, where delta K is the Fourier transform of the density contrast delta R, defined more precisely in equation 1.12 below, and denotes an average over co-orientations. The direct delta delta to the power of 3 K minus Capri, not to be confused with the delta that denotes the perturbations, means that modes which different K is not equal to Capri happen to be statistically independent. This property can be understood from inflation, a theory that predicts average statistical properties encoded in pK. Since pK is a Fourier transform of the density self-correlation function, it conveniently expresses in Fourier space in the homogeneity in matter distribution in the physical space. A large small value of pK means that there exist many few structures with the characteristic size is equal to 1 divided by K. The measurement shown in figure 1.5 with the right therefore show the universe has some power on all scales. It's not restricted to one scale, and there is no reverse engineering to diminish or reduce the power on all angles and scales. To make the clumpiness of the universe even more apparent, sometimes pk, which has units of the length to the power of 3, is rescaled into the dimensionless variant. It means that whenever you want to have a reverse engineering, it is enhancing and amplifying its um, own power, and as a re-escalating, as a reconfigurably to dimensionless variants, but it's about delta to the power of k is equal to k to the power of 3 pk divided by 2 p to the power of 2. Small values of delta to the power of 2 correspond to small density contrasts. While delta to the power of 2 is equal to 1, for instance, indicates an over density comparable to the average. A quick manipulation of the pK data in figure 1.5 middle right shows that indeed delta to the power of 2 rises to large values in the large core region. In other words, the data show that the universe exhibits large inhomogeneities on small scales, large core. In a standard cosmological model, the primordial inhomogeneities are generated from inflation with small amplitudes delta is equal to 10 to the power of minus 5. This is confirmed from the near perfect smoothness observed in the CMB, which essentially provides a photo of photon content of the universe second when photons last scatter. So you're watching the figure 1.5, the power spectrum of the CMB acoustic peaks, middle row left is extracted from the map of temperature on its tropic top left. The matter power spectrum, middle row right is extracted from the extensive galaxy surveys top right, as well as from other mapping probes. The same quantities in the absence of dark matter are illustrated in the bottom row. This poses a question: how could the tiny primordial inhomogeneities grow from such a small amplitudes to the large contrast that we observe today? The answer, as anticipated above, is that the growth of the density perturbations is crucially driven by the presence of dark matter. In order to quantitatively understand how that happened, we need to sketch their evolution in the early universe. Let us consider a universe filled with a generic matter fluid whose exact nature will leave for the moment unidentified. The main features of the evolution of the density perturbations of such a medium can be understood by approximating the full general relativistic computation with its Newtonian limit. This is a valid description of non-relativistic matter at length scales smaller than horizon. A non-relativistic fluid is fully characterized by its density rho RT, by its velocity field nu RT, and by the equation of states for the pressure rho. Its gravitational interactions are described by the Newton potential field. These quantities are governed by the evolution Euler equation, and the derivative of rho based on the time is equal to delta rho nu is equal to 0 when there is a continuity, and delta nu based on the time plus a nu multiplied by delta nu is equal to minus delta pressure divided by density minus delta phi when the Newtonian law described the acceleration is equal to force divided by mass, and delta to the power 2 phi is equal to 4 p which form a system of nonlinear differential equations. For a quasi-homogeneous universe, it is possible to gain useful analytic information by expanding the above quantities as the first-order perturbations to the zero-order homogeneous background. Rho is equal to rho 0 t plus rho 1 xt, and pressure is equal to pressure 0 plus pressure 1. Nu or velocity is equal to nu 0 plus nu 1. Phi is equal to phi 0 plus phi 1. We first consider the case of a static universe. No expansion equations 1.6 reduced to a set of coupled equations for the perturbations. Delta p rho 1 based on the time is equal to rho 0. Delta nu 1 is equal to 0. And delta nu 1 based on the time plus nu s to the power of 2 divided by rho 0. Delta rho 1 plus rho delta phi 1 is equal to 0 when we have a static universe, and delta to the power of 2 phi 1 is equal to 4 pga rho 1, where we defined the equality nu s to the power of 2 is equal to delta pressure based on the density is equal to the pressure 1 divided by density 1, which is interpreted as the standard speed in the fluid, as we will see in a moment. By acting with these derivatives on the first equation, the performing appropriate substitutions in it using the second and third equations, one arrives at the evolution equation for the density perturbations rho 1, for example, the Jeans equations. The derivative of the rho 1 divided by the second derivative of the rho 1 based on the time minus nu s to the power of 2 delta to the power of 2 rho 1 is equal to 4 p g p rho 0 rho 1 ignoring gravity, for example, setting g is equal to 0. The solution are density waves, for example, sound that travels at the speed nu s, including gravity. The full equation expresses the competition between a pressure term on the left hand side and a collapse term on the right hand side. The gene length lambda j is equal to square root nu s to the power of 2 divided by 4 pga. Rho 0 discriminates which term is dominant. Perturbations on larger scales, lambda is greater than lambda j collapse and grow in time, while perturbations on small scales, lambda is smaller than lambda j, are supported by pressure. The growth with time of the collapse modes is exponential. Rho 1 is almost equal to e to the power of square root 4 pg rho 0 t, as one can easily check by solving the differential equation 1.9 for nu s tends to 0. This is the gene instability that, when applied to normal matter, explains how gas clouds collapse to form compact bodies, for example, stars. The intuitive meaning of the gene scales is that a cloud of gas collapses when it is so big and that its hydrostatic pressure, which prevents the collapse on time scales, tau pressure is equal to lambda j divided by nu s, is too slow to stop the gravitational attraction which clamps it on a timescale. Star gravity is equal to j rho 0 to the power of minus 1 divided by 2. One can also define the gene mass as mj is equal to 4 p rho 0 lambda j to the power of 3 divided by 3. For example, as a mass enclosed in a sphere of radius lambda j. Perturbations with mass is greater than mj are gene unstable and collapse. We move next to this case of an expanding universe. Solving the zero order quantities describing the smooth background gives the Hubble expansion. Rho 0 t is equal to rho 0 t 0 divided by alpha to the power of 3. Now 0 is equal to Hubble expansion multiplied by r, and delta phi 0 is equal to 4p g rho 0 divided by 3r. So far, IT, the usual scale factor of the universe, has been left with an unspecified time dependence. Solving equations 1.6 would determine the expansion IT of a matter dominated universe. In general, extra components, radiation, and cosmological constant contribute to the expansion, and IT is given by the fully relativistic Friedmann equations. See Appendix C. The first relation in the 1.10 is just the standard dilution of non-relativistic matter when the volume expands by factorial alpha to the power of 3. The second relation is the Hubble law for the velocity field of the homogeneous background with respect to which the perturbations, the new one, can be seen as peculiar velocities. The third is the solution to the Poisson equation, applying the Gauss theorem to a sphere with radius r center at the origin and ignoring the infinite amount of its outside matter. This logical jump, known as the Jeans symbol, is justified thanks to the existence of a horizon in the full relativistic treatment. Expanding equation 1.60 of first order imperturbations leads, after tedious but straightforward derivations, to the linear equation derivative rho 1 based on the time plus 3 times Hubble expansion rho 1 plus Hubble expansion r delta rho 1 plus rho 0 delta nu 1 is equal to 0. Delta nu 1 based on the time plus Hubble expansion nu 1 plus Hubble expansion r delta nu 1 plus nu s to the power of 2 divided by rho 0. Delta rho is 1 plus delta phi 1 is equal to 0. When we have an expanding universe, six short terms in equation 1.11 is compared to equation 1.8 are identified by the appearance of Hubble expansion, which is completely related to the entropy. This is why, in one hand, we have a Hubble expansion, and the first capital letter is H, and another reason is somehow because both of them are talking about the expansion of the universe, and it has a direct correlation and covariant with the entropy. Next, we define the relative density or density contrast delta R and expand it in co-moving Fourier modes, and delta R is almost equal to rho 1 R divided by rho 0 is equal to integral the third derivative called 2p to the power of 3 delta k t exponential minus I k x, where x is equal to r divided by t. The rescaling of the space vector by factor it means that the wave number 1 divided by k follows the average evolution of the universe. This is convenient because in this way equations for modes delta k with different k turn out to be decoupled. Similarly, we define nu k and phi k, the Fourier transforms of the velocity perturbation nu 1 and of their gravitational potential phi 1. Fourier space equation 1.11 becomes as 1.13 delta k, the derivative of the delta k based on the time minus I k divided by r multiplied by nu k is equal to 0. And when we have expanding the universe, the derivative alpha nu k divided by based on the time minus I chi nu s to the power of 2 delta k minus I chi phi k is equal to 0. Phi k is equal to minus 4 pg rho 0 divided by k to the power of 2 alpha to the power of 2 delta k. The second equation 1.13 can be simplified further. One can decompose the velocity perturbation as nu 1 is equal to nu 1 perpendicular plus nu 1 is parallel, where delta nu 1 perpendicular is equal to 0 divergence free or solenoidal component, and delta multiplied by nu 1 parallel is equal to 0 curve free or irrotational component in Fourier space. K multiplied by nu k perpendicular is equal to 0. K multiplied by nu k parallel is equal to 0. The second equation in 1.13 for nu k perpendicular just amounts to delta m r nu k perpendicular divided by delta t is equal to 0, giving the nu k perpendicular is equal to 1 divided by r. The solenoidal component nu k perpendicular therefore dies away with the expansion of the universe. So, and only the irrotational component nu k parallel survives. Since nu k parallel is parallel to k, we can substitute everywhere in equation 1.13. Nu k tends to nu k coupling, where coupling is the unit vector along k, and k tends to absolute k is equal to k. At this point, we can combine the three equation 1.13 into one second order equation by taking nu k from the first equation, plugging it into second, and using phi k from the third arrives at these equations. So until now, thank you so much for watching my tutorial video until the end. If there is any simulation for this literature, you can find it from github.com master script /koshi script or safro script. Today is the 12th day of the August 2026, and time is near the morning. Today is the one sort of phenomenon which is related to our literature is expanding and expansion of the universe, which is completely related to the entropy.